On March 30th, 2026, Google Quantum AI published a resource estimate for attacking Bitcoin's elliptic curve signatures on SEC P256K1. Their number comes in at roughly 20 times fewer qubits than prior published estimates. The headlines ran with that as a $600 billion countdown clock. The paper itself is more careful. Today, we walk through what the researchers actually found, what they did not say, and what is already being done about it. Before we get into the science, let us look at what the media did with this paper. Because the gap between the headlines and the actual findings tells you a lot about how quantum computing gets covered. CryptoSlate ran with a $600 billion countdown. On X, Post went further, declaring Bitcoin already broken and Q-Day already here. The mainstream headlines compressed a resource estimate, which is a calculation of what a hypothetical machine would need, into a countdown clock. The social posts went past compression into outright misreading. The timeline did move. What did not move is the existence of the machine that would actually run the attack. That distinction is what most coverage flattened. This is not a fringe paper. 9 authors from Google Quantum AI, Stanford, UC Berkeley, and the Ethereum Foundation contributed. Justin Drake is an Ethereum Foundation researcher who helped initiate their post-quantum effort. The research is credible. The question is what it actually says. Let us start with the core result. But before the numbers, one piece of vocabulary that everything else hangs on. Quantum hardware today gives you physical qubits. They are noisy. To run an algorithm reliably, you combine many physical qubits into a single logical qubit using an error-correcting code. The Google paper assumes the surface code at a physical error rate of 10 to the -3. Dividing the paper's own numbers, 1,200 logical qubits, mapping to under 500,000 physical qubits, works out to roughly 400 physical qubits per logical qubit across the full compiled attack. That ratio averages data qubits, ancilla, and magic state factories together. It is not the surface code's per qubit overhead on its own. Hold on to that mapping. Hundreds of physical qubits for each logical qubit. The paper's central result is a resource estimate for solving the elliptic curve discrete logarithm problem on SEC P256K1, the specific curve that secures Bitcoin, Ethereum, and most cryptocurrency wallets. They found 2 configurations. The first uses fewer than 1,200 logical qubits, with 90 million Toffoli gates. The second trades qubits for gates. It needs fewer than 1,450 logical qubits, paired with 70 million Toffoli gates. When you map either configuration onto a superconducting surface code architecture at a physical error rate of 10 to the -3, you get fewer than 500,000 physical qubits. This chart shows the trajectory. In 2022, Weber and colleagues estimated 13 million physical qubits for a 24-hour attack. In 2023, Litinsky brought that down to about 7 million, using a silicon photonics-inspired architecture. In 2026, Google brought it under 500,000. That is roughly a 20 times reduction versus those prior published estimates, consistent with Google's approximately 20-fold framing. And the key insight is that this improvement comes from algorithmic optimization, not from building a bigger machine. The authors refined the quantum circuit layout for elliptic curve arithmetic and reduced the ancilla qubits needed for modular inversion. Same attack, tighter budget. Here's where it gets interesting for Bitcoin specifically. The low-gate variant of the attack could run in about 9 minutes from a primed state. Bitcoin produces a new block every 10 minutes. Figure 6 of the paper shows this gives an attacker approximately 41% success probability per block interval. But this assumes an attacker-favorable model, a single signature target, fast public key propagation, and no network-level defenses. These are theoretical numbers under idealized conditions, not operational certainty. Here is how that race plays out. The full bar is Bitcoin's 10-minute block interval. The red zone is the 9-minute attack window. A transaction is broadcast. The attacker extracts the public key, runs the quantum computation, and hopes to finish before the block confirms. And here's the qualifier that the headlines leave out. This entire analysis describes a fault-tolerant quantum computer running a surface code architecture with full error correction. This is not a near-term, noisy, intermediate-scale quantum device. No such fault-tolerant system has been built, and the authors are explicit about this. The paper is a resource estimate. It answers the question, if you build this machine, what does the attack cost? It does not answer when that machine will exist. Those are fundamentally different questions. So the attack needs 500,000 physical qubits. Where does quantum hardware actually stand? Let us look at the numbers. This diagram shows the gap between where quantum hardware stands as of 2026 and where it needs to be for this attack. IBM's largest announced prototype, Condor, reached 1,121 physical qubits as a scale milestone, while IBM's production processors are Heron family chips at 156 qubits. Google's Willow has 105. The paper's attack requires fewer than 500,000 physical qubits. Even against the 1,121 qubit Condor prototype, the gap is about 446 times, and none of these machines implement the fault-tolerant error correction the attack assumes. As of 2026, the largest demonstrated logical qubit system is a 96 logical qubit neutral atom processor from Quora, Harvard, and MIT, published in Nature in January 2026. IBM's published fault-tolerant roadmap targets about 200 logical qubits by 2029 with its Starling system. Both are still short of the 1,200 to 1,450 logical qubits this attack needs, a 12 to 15 times gap from today's record, which translates to a much larger gap in the physical qubits needed for error correction overhead. Scaling from the low hundreds to the low thousands of logical qubits involves unsolved engineering problems in wiring density, cryogenic cooling, and error correction. These are not software problems you can optimize away. They are physical engineering challenges. Mining is not under threat. One common misconception: quantum computing does not threaten Bitcoin's proof of work. SHA-256 hashing, which secures proof of work, is resistant to Shor's algorithm. The threat is specifically to ECDSA and Schnorr signatures on SECP-256K1. A separate paper by Dallaire du Mur examined quantum mining and found it would require on the order of 10 to the power of 23 physical qubits and 10 to the power of 25 watts of power. To put that in perspective, 10 to the power of 25 watts is an absurd amount of power. Quantum miners are not a realistic concern. Now, here is something most coverage of this paper completely missed. Bitcoin's vulnerability depends not only on the signature scheme, but on how public keys are stored on chain. Pay to public key, hash, and pay to witness. Public key hash addresses store a hash of the public key, not the key itself. The actual public key is only revealed when the owner creates a spending transaction. This means a quantum attacker would need to extract the key from a broadcast transaction and break it before the transaction confirms. That is a much harder timing constraint. Pay to Taproot addresses work differently. They expose the tweaked public key as an elliptic curve point on chain, while the coins remain unspent. This gives a quantum attacker an indefinite window to work on the math offline. Here's the difference visually. On the left, traditional address types keep the public key tucked behind a hash. No attacker sees the key until you go to spend. On the right, Pay to Taproot puts the key directly on chain, tweaked but exposed, even while the coins sit unspent. No race against block confirmation. Any P2TR unspent output is a standing target. This tradeoff was known at the time. Bitcoin developer Luke Dash Jr. posted a warning to the Bitcoin dev mailing list on March 15, 2021, titled PSA, Taproot Loss of Quantum Protections. The community accepted the tradeoff because the quantum threat seemed distant. The Google paper tightens the resource estimate, making the Taproot exposure more salient than it appeared at the time of the 2021 post. It is not a timeline forecast. According to the paper's Table 1, P2TR outputs moved approximately 16.8 million BTC in 2025 and separately accounted for 21.68% of all Bitcoin transactions that year. Two different measures. One is volume, the other is share of transactions. As Taproot adoption grows, so does the amount of Bitcoin held in quantum-exposed outputs. The good news is that the cryptographic community is not sitting still. Multiple blockchains already have post-quantum signature support in production or on testnets. On the standard side, NIST finalized FIPS 203, 204, and 205 in August 2024. These provide standardized post-quantum algorithms for key encapsulation and digital signatures. MLChem for key establishment. MLDSA, formerly known as dilithium, for digital signatures, and SLHDSA for stateless hash-based signatures. The standards infrastructure to support wider adoption has been in place since 2024. For Bitcoin specifically, BIP 360, led by Hunter Beast, defines a new output type called pay-to-Merkle root. It was merged into the BIP's repository on February 11, 2026 as a draft proposal. Publication in the BIP's repo does not imply community consensus or activation. BTQ says its version 0.3 testnet, deployed on March 19, 2026, is already testing dilithium, that is MLDSA-based, transactions on a Bitcoin fork. That comes from BTQ's own announcement, not a neutral standardization source, so treat it accordingly. This timeline shows the broader picture. The quantum-resistant ledger has run on XMSS signatures since its mainnet launch in June 2018. Algorand shipped Falcon 1024 post-quantum transactions on its mainnet in November 2025. Solana and Project 11 prototyped a post-quantum signature testnet in December 2025, later described by Project 11 as implementing MLDSA as an EDDSA replacement. And the Ethereum Foundation formed a dedicated post-quantum team in January 2026, led by Thomas Karatjer, and launched two $1 million research prizes. Justin Drake, one of the 9 authors on the Google paper, is an Ethereum Foundation researcher who helped initiate this effort. But here's the cost. An MLDSA 44 signature is about 2,420 bytes. That is roughly 33 times a 72-byte ECDSA signature, and roughly 38 times a 64-byte Schnorr signature. Other MLDSA parameter sets are larger still. Every transaction grows, with direct implications for block space, fees, and throughput. The pattern across all these projects is consistent. Post-quantum signature schemes exist, and they work, but integrating them into production blockchains is slow. You need changes to consensus rules, wallet ecosystem updates, and years of testing. The algorithm is the easy part. The migration engineering is the bottleneck. For Bitcoin specifically, any change to the signature scheme requires a soft fork, community agreement, and wallet updates across the entire ecosystem. That process takes years. So what should you take away from all of this? Let us put the pieces together. The Google paper does not mean Bitcoin is broken. It means the cost of a future attack is lower than we thought, and the engineering timeline for defense needs to account for that. The window to act is measured in years, not minutes. But years is exactly the lead time that protocol upgrades, key rotations, and standard adoptions require. The worst outcome would be treating this paper as either proof of imminent doom or as irrelevant because the hardware does not exist yet. Both readings miss the point. And the threat extends well beyond cryptocurrency. Store now, decrypt later means adversaries are harvesting encrypted traffic today with the intent to decrypt it once quantum computers are capable. This applies to TLS sessions, VPNs, classified communications, and any data that needs to stay secret for years or decades. This paper's tighter resource estimate makes that timeline harder to dismiss. The 500,000 qubit number is not just a Bitcoin problem. It is a signal for every system that relies on elliptic curve or RSA cryptography. To summarize, the hardware gap is enormous. About 446 times between IBM's 1121 qubit Condor prototype and the attack threshold. The Google paper is a resource estimate, not a timeline prediction. It tells us what the attack costs, not when it becomes possible. Taproot creates a standing target for quantum attackers, and that is something most coverage completely missed. Migration is underway across multiple chains, but the engineering bottleneck, not the cryptography, is the real challenge, and the window to act is measured in years. But that is exactly how long these protocol upgrades take. This is not a reason to panic. It is a reason to act. That is the real state of the quantum threat to Bitcoin. If this helped, subscribe for more deep dives into post-quantum cryptography. The full article and the Google paper are linked in the description. Spread awareness, not fear. I hope this was useful. Hit like and subscribe for more on post-quantum cryptography and zero-knowledge proofs.